So welcome back. In today's lecture, we will be discussing visualizing molecular vibrations using internal coordinates. So let us start the lecture. So what do you mean by visualizing molecular vibrations? So for example, in case of water molecule, in the last lecture, we have seen that symmetry of normal modes of vibration. We saw that there are three vibration modes present, and the symmetry we could find out was A1 and A1 and B1. So there are two A1 modes and one B1 mode, right? But we don't know how does it look on the molecule. So can we use our knowledge of symmetry and group theory to visualize these molecular vibrations? So yes, we can do that if we use internal coordinates. So what are internal coordinates? So we have seen that if we use Cartesian coordinates on each atom, we can actually get to know the symmetry of normal modes. We can see the symmetry of translational, rotational, as well as vibrational modes, but we cannot visualize them. So if we use internal coordinates, we can actually visualize these vibration modes. So what are internal coordinates? So internal coordinates are that will define vibrations. These are bond distances, or you can say change in bond distance also, are bond angles, which is theta, and torsional angles. So torsional angles, let us say these are phi. So bond distances, to define bond distances, you need 2 points or 2 atoms, right? To define a bond angle, you need 3 atoms minimum. And to define a torsional angle, you need 4 atoms minimum. Okay. So that is the requirement. So that means if you have a diatomic molecule, you cannot have any bond angle or torsional angle. You can only have bond distances. Similarly, if you have triatomic molecule like water, you cannot have torsional angle. You can only have bond distances and bond angles, right? So let us take internal coordinates and see what do we get, like how do we visualize molecular vibration. So let's start with drawing water molecule. So let's say if I have change in bond length as delta R1 over here, and then this would be delta R2, and this will be my change in bond angle delta theta, right? So now if I take the bond angles and bond distances as the basis and create a reducible representation, let us see what do we get. So we will use internal coordinates one by one. Okay, that is very important. You cannot take bond angle and bond length together and create a reducible representation. That would not solve the problem. So one by one, and create a reducible representation. So what do we get? So we have C2V point group, E C2Z, sigma XZ, and sigma YZ. Now if I have tau R1, R2, this will be, so these two bonds are now the basis. So E will have 2, C2Z will be 0 because both the bonds are moving, getting replaced with one another. Sigma XZ, again the bonds are getting reflected. So remember that this is my X, Y, and Z. So my XZ is perpendicular to the plane of the board. So this is 0. Sigma YZ, both the bonds stay at where they are, right? Similarly, we can create one for tau theta. So reducible representation using delta theta as the basis. So this will be, nothing will change for this angle, right? This will be 1 1 1 1. Okay, so now this reducible representation can be broken into its component irreducible representations, which will be, so we can say R1 R2 is equal to A1 plus B1 using reduction formula. So I'm sure you all know how to do this now, so we are not going to go to details of this. Similarly, tau delta theta is equal to A1. That is very, very clear from here itself. So by looking at the character table, you know that this is the symmetry of totally symmetric representation, even. So now what we do is, now we will use projection operator on various internal coordinates. So that means, so we will do projection of A1 onto delta R1. So this will give me, I'm sure you all know how to calculate this. So for A1, I will have 1 into E applied on R1 or delta R1 plus 1 into C2Z onto delta R1 plus 1 into sigma xz onto delta R1 and this H comes from the F4 comes from the H, 1 by H, right? So this gives me 1 by root 2 after normalization delta R1 plus delta R2. This is after normalization. See, this is a 1D representation A1. So you will get only one linear combination of the basis sets that will give you one normal mode, right? Now, similarly, if I do on projection operator B1, which comes from again from the tau R1 R2, then this is on delta R1, what do I get? So I'm not going to write the detailed calculation. Now I will get delta R1 minus delta R2, right? So this linear combination is obtained when you apply the projection of B1 symmetry onto delta R1, right? So let us also do it for, okay, so let's see. So the stretching vibrational modes are therefore the stretching so A1 means it's a symmetric linear combination of delta R1 and delta R2, right? So because both are positive, with both positive, right? We have delta R1 positive and delta R2 positive. Now what is B1? B1 is antisymmetric linear combination of delta R1 R2 where one is positive and other is negative. Okay, so that means what I can write is, so I can say that my one of the vibrational modes, nu 1 is for the frequency which has A1 symmetry, can be written as 1 over root 2 delta R1 plus delta R2. Now visually, how does it look? So if I try to draw it on water molecule, I can say both the bonds are stretching, right? because both of them are positive. Delta R1 and delta R2. Now similarly, if I want to write the second stretching mode, then this will be nu 1 B1, which will be equal to 1 over root 2 delta R1 minus delta R2. And now I can say that one of the bond is stretching and the other is compressing. This is my second vibrational mode. So similarly, we can visualize how it looks for bending mode. So let's do it for bending mode. So if I apply projection with A1 symmetry onto delta theta, we have only one basis vector in this case, delta theta. So we will say what do we get is delta theta plus delta theta plus delta theta plus delta theta, which gives you delta theta overall, right? So the only bending mode which is possible here is that the two protons will move like this, right? So there is a change in the angle like this, increase or decrease. So that's the only bending mode which is possible. Now let us consider one more example so that the procedure is clear, and then let's go to a little complex example than this. So another example, let us now consider NO3 ion. So the NO3 ion looks like we have an overall negative charge onto this, right? The point group is D3H here. So now let's start with finding the symmetry of vibrational modes. So D3H, you have A2C3, 3C2, sigma H, and then 2S3 and 3 sigma V's. Now for this we get from XYZ, so tau XYZ, which is the summation of all IR representation where X, Y, and Z is the basis, right? So this we will get directly from character table 3, 0, minus 1, 1, minus 2, 1. And then number of unshifted atoms. So this will be 4 here. C3, it will be 1. Central atom will be unshifted. C2, 2 atoms will remain unshifted. Sigma H, all 4 will be unshifted. S3, 1 atom will be unshifted. And then sigma V, 2 atoms will be unshifted, right? Okay, so that gives me tau 3n. Multiply these two. So I'll get 12, 0, minus 2, 4, minus 2, 2, right? Now upon reduction of this, tau 3n can be broken into the component IRs using reduction formula. So this will be A1 prime plus A2 prime plus 3E prime plus 2A2 double prime plus E double prime, right? Now from here I can calculate tau vibrational, which will be tau 3n minus tau translational, which will be all XYZ, and tau rotational, all RX, RY, RZ, IRs, right? Tau rotational. So this leaves A1 prime plus 2E prime plus A2 double prime. So this is the procedure to obtain symmetry of all the normal modes of vibration. Now what we have to do is we have to use internal coordinates to find out, to help visualize this. So let's start with the change in bond length. So we have N, O, O, O. So we have delta R1, delta R2, delta R3. So if I create under D3H tau R1, R2, R3, and this will be D3H. So I will see that I'll get a representation like 301, 301, right? And now I can reduce this to get the component IRs, component irreducible representations. So if I do that, tau R1, R2, R3 is broken up into A1 prime plus E prime using reduction formula. Now we'll use projection operator of this symmetry onto one of the basis sets, right? One of the functions in the basis set. Using projection operator to find linear combinations of delta R1, delta R2, delta R3. So first one is very simple. If we do totally symmetric representation projection operator, what you will get is upon normalization. So again, I'm not going to go into details of how to apply projection operator. That should be fairly simple by now. Delta R1 plus delta R2 plus delta R3. Okay, so that means all the bonds are increasing in length. This will be called as symmetric stretching. And you can draw it like that all the bonds are increasing in length symmetrically. This is, you can call it as nu 1 with A1 symmetry, A1 prime symmetry. So this is nu 1. So now similarly for other stretching vibrations, E prime delta R1. This if you do, so you will get 1 over root 6, 2 times delta R1 minus delta R2 minus delta R3. Okay, so this can be called as nu2 second mode stretching mode with E prime symmetry, right? And now you can draw it as one of the bonds is increasing in length and the other two bonds are compressing, right? So these are getting shortened, this is getting increased, right? So this will be second mode. Now you should get two linear combinations here which are orthogonal to each other. We have already got one. So how do you get the second one? To get the second one, again it is not trivial and you need to use hit and trial. So one of the methods is to apply, so there are, if you remember, there were three rules. So if we apply any operation, applying any operation, symmetry operation of the group on the above function, it must lead to, there are three options, right? Plus or minus of itself, you'll get the function back with plus or minus sign. The second will be plus or minus another, you may get lucky and you will get a degenerate function, the second function which you are looking for. Or third is a linear combination of these degenerate functions. Okay, so let us do it. Let us try to do a symmetry operation onto this function and see what we get. Okay, so let's see, let's pick up C3 out of D3H point group and apply it on this particular function. So 2 delta R1 minus delta R2 minus delta R3, right? So if you apply this, what you will get is 2 delta R3, R1 goes to R3, R2 goes to R1, delta R1, delta R2, right? And let's call it as function P. Now we have to test whether P and nu2, which we got earlier, nu2 E prime, are these orthogonal. So to test the orthogonality of two functions, whether they are degenerate or not, we'll get to know if they are orthogonal or not, right? So let's do that now. How do you do that? So we'll have to multiply the coefficients of different functions in this, different basis vectors. So delta R1 coefficients multiplies with the delta R1 coefficient here, and delta R2, delta R2, delta R3, delta R3, and then take summation over all and see if you are getting 0 or not. So for delta R1, I have minus 1 here and 2 here, plus minus 1 here and minus 1 here, plus 2 here and minus 1 here. So this becomes minus 2 plus 1 minus 2. So this is not equal to 0. So it is not orthogonal. So I'm just giving you another way of finding these orthogonal functions in case of degenerate IR representation. So let us now do a C3 square operation onto the same. This was 6. 1 over root 6 onto 2 delta R1 minus delta R2 minus delta R3. Now what do I get here? I'll get 2 delta R2 minus delta R3 minus delta R1. Let us call this Q. Again, let's test the orthogonality, whether we are getting any orthogonal function or not, of Q and nu2 E prime. So what do we get here? So we will see that Q dot nu2 E prime is not equal to 0. So again, this will be not orthogonal. Okay, so now what do I do? So let us do a hit and trial. Let us subtract P minus Q, and what do we get here? We will get, after normalization, 1 over root 2 delta R3 minus delta R2. Okay, now let us call it as R. So now let's test the orthogonality between R and nu2 E prime. So that will give you R nu2 E prime. This will give you delta 2. Delta R2 has minus 1 here, and it had minus 1 there, plus 1 into minus 1, and this goes to 0. So that means R can be treated as nu3. So that means R is equal to nu3. So the third vibrational mode which we are looking for. So this means that you can say that my N, one of the bond is not changing, another bond is increasing, and another bond is compressing, right? So this is my, and this has symmetry as E prime. This is my third stretching vibrational mode, right? So, but this is a cumbersome method to find out as we have discussed earlier, there is no definite way of finding one. So let's try to do it in a different way. Let us look at one more way of finding the degenerate function. So now let's consider that upon, so let's say nu3 e prime can be written as linear combination of nu2 e prime and some alpha times p, which we have obtained earlier, right? When we applied C3 onto this, we obtained linear combination which was termed as p. So now if you consider this, then it is possible, right, that the two can be a linear combination. This can be a linear combination of any linear combination, and we can find out alpha. Okay, so let's do that. Delta R1 minus delta R2 minus delta R3 plus alpha times 2 delta R3 minus delta R1 minus delta R2, right? Now this gives me 2 minus alpha. Let us now separate the variables. So 2 minus alpha delta R1 plus minus 1 minus alpha delta R2 plus 2 alpha minus 1 delta R3, right? Now this is my nu3 e prime, and the normalization coefficient can be written as, because these were not normalized, so we need to normalize it. So the square root of sum of squares of the individual coefficients. So we can write 2 minus alpha square plus 1 plus alpha square plus 2 alpha minus 1 square. Okay, now if we can simplify this, what do we get? 2 minus alpha delta R1 minus 1 plus alpha delta R2 plus 2 alpha minus 1 delta 3 divided by 5 alpha square minus 6 alpha plus 6 square root. There is only one variable here, right? So now, and I know that using orthogonality condition, between nu2 and nu3, so both are e prime symmetry, right? So nu2 e prime dot nu3 e prime should be equal to 0. So now I can equate the coefficients, multiply the coefficients and equate it to 0, and what do I get? So I will get 2 by root 6 into 2 minus alpha. So actually this normalization is not required, so we can directly put it to, because this will be a common factor in all three, so this will go to 0 anyways, right? So it's not required to put it here. Plus 1 plus alpha and plus minus 2 alpha plus 1 equal to 0, and this gives me alpha is equal to half. So now substituting this value of alpha in here, I will get a normalized nu3, which is nothing but nu3 e prime, which is nothing but 1 by root 2 delta R1 minus delta R2. Right? So I'm getting a different form here, but R1, R2, R3 are interchangeable, so it does not really matter whether I'm getting R2 minus R3, R3 minus R2, or R1 minus R3. So the point is that one of the bonds is increasing in bond length and another bond is decreasing in bond length, right? So that finishes up. stretching mode, visualizing stretching mode. Now the next part here is the bending mode. So in case of a planar molecule like this, there is also a possibility of out of plane bending and in plane bending. So I will leave up to you that what kind of internal coordinates would you choose to devise a tau reducible which can define the in plane bending as well as out of plane bending. So you already know that you have already covered out of tau vibrational modes A1 prime and E1 prime. So you have defined it for this. Now what you are left with is A2 double prime and another E prime, right? So this is stretching that we have already seen. Now this portion is left for bending modes. Now bending modes, I leave it as home assignment. So try to do it for yourself. Otherwise, we will discuss in the interaction session. Okay. So this finishes up. I'm deliberately leaving it for you to do it so that you get some idea of what angles to be chosen as internal coordinates and what angles will define the bending mode. There is a possibility of in plane bending and out of plane bending and all, right? So this finishes up visualization of the vibrational modes, and we have seen that how group theory is helpful in doing that. And the last lecture now is on spectral transition probabilities. That will be coming up later. That's all.